Why do we search? The question itself is a fundamental current of the human spirit, an ancient and persistent driver of our species, as primal as the need for food or the instinct to build shelter. It is the same impulse that led mariners to sail beyond the edge of the known world, not merely for conquest or for gold, but for the raw, unfiltered knowledge of what lay beyond the horizon. It is the restless curiosity that fuels the engine of science, the relentless urge to illuminate the quiet voids of our understanding with the light of discovery. We turn our gaze to the stars and ask a question that has echoed through millennia of human thought. A question at once profoundly scientific and deeply personal: are we alone? This is not merely a search for biology, for microbes clinging to life in a subterranean ocean or lichens spreading across a frozen rock. It is a search for biology that has awakened, for matter that has become clever enough to organize itself into a mind capable of contemplating the universe that spawned it. If we were to find such a civilization, the implications would be staggering. A shockwave that would ripple through every aspect of our culture, our philosophy, our very sense of self. The detection of a single, unambiguous, artificial signal would answer 1,000 existential questions in an instant. It would tell us that life is not a cosmic fluke, that intelligence is not a singular, terrifying accident, and that survival on a galactic timescale is, at least, possible. It would reframe our entire story, transforming us from cosmic orphans into the newest members of a galactic community. The search for extraterrestrial intelligence is a peculiar and noble form of science, one that operates outside the familiar textbook method. It is not a process of proposing a hypothesis and then attempting to falsify it. You cannot, with any amount of data or logic, prove the negative on this scale. You cannot demonstrate that intelligent life is not out there. The vastness of the cosmos and the depths of time make such a proof impossible. You can only do one thing. You can only discover that it is. This is the nature of discovery science. It is a patient vigil, a long listening. And on one quiet summer night, for a fleeting 72 seconds, it seemed as if that vigil had ended. A signal arrived. A whisper from the void, so powerful and so perfectly formed that it defied all natural explanation. It was not a message in a human sense, not a string of translatable words, but a sequence of 50 numbers and letters printed out on a continuous sheet of paper. A ghost from a bygone era of computing. Yet it remains the most profound and tantalizing clue humanity has ever received. 6 E Q U J 5. It appeared once, a transient, focused beam from an unknown source in the constellation Sagittarius, and was never heard from again. It has become an artifact of scientific folklore, a single, unexplained data point that continues to haunt the long silence of the search. It was the strongest signal ever recorded, an enormously powerful, narrow-band transmission that looked exactly like what we were looking for. And in its wake, it left a beautiful, aching mystery, a testament to the fact that sometimes the most compelling truths are found not in what we know, but in what we can never fully explain. The universe speaks in a language of light, but our eyes, the primary instruments of our perception, are attuned to only a tiny fraction of its vast and complex vocabulary. We are most familiar with optical astronomy, the ancient science of capturing visible light with telescopes to magnify distant objects. It is a practice born from the first moment a human ancestor looked up and wondered at the points of light scattered across the darkness. But the visible spectrum, that beautiful rainbow of colors our brains are wired to interpret, is an astonishingly narrow sliver of the full range of cosmic expression. The electromagnetic spectrum stretches from the high-energy fury of gamma rays and X-rays The violent signatures of exploding stars and matter-devouring black holes, down to the low-energy, pervasive hum of infrared and radio waves. To see only invisible light is to walk through a vibrant, bustling metropolis while wearing blinders and earplugs, aware only of the sliver of reality directly in front of you, oblivious to the rich, layered tapestry of life and sound unfolding all around. Radio astronomy is the art of removing those blinders, of tuning our senses to the invisible chorus of the cosmos. Every star, every galaxy, every swirling cloud of interstellar gas produces energy across this entire spectrum. And the radio end holds a wealth of information that optical light cannot convey. It is in these long, low-energy waves that we can perceive the universe in a different state, hearing the hum of its fundamental processes, the echoes of its creation, rather than just seeing the flash of its brightest, most energetic moments. This ability to listen to the hidden universe was born in the early 1930s, when a scientist named Carl Jansky, working for Bell Labs, stumbled upon one of the most significant discoveries in the history of astronomy. He had built a large, rotating antenna, a contraption that looked like a skeletal Ferris wheel, to track the source of the persistent static that interfered with transatlantic radio communications. As he meticulously tracked the noise, he found that it rose and fell on a cycle of 23 hours and 56 minutes, the exact length of a sidereal day, the time it takes for the Earth to complete one rotation relative to the distant stars. He had discovered that the hiss was not coming from Earth, but from the heavens. He had pinpointed its source to the dense, bright center of our own Milky Way galaxy. For the first time, humanity had an ear to the cosmos, and the sky was not silent. This monumental discovery, however, was slow to ignite a revolution. It was a radio engineer from Wheaton, Illinois, a man named Grote Reber, who truly carried the torch of this new science. In his own backyard, with a 30-foot dish antenna he designed and built himself, Reber spent a solitary decade as the world's only active radio astronomer. Night after night, he painstakingly scanned the Milky Way, producing the first-ever maps of the radio sky. His work was a labor of pure passion, laying the foundation for a new branch of science, and his homemade antenna became the conceptual blueprint for the colossal radio telescopes that would follow. The Second World War, for all its devastation, was a catalyst for incredible technological advancement, particularly in electronics and radar. In the war's aftermath, as nations began to rebuild, a new era of scientific ambition took hold. The United States, locked in the early stages of the Cold War and the space race, was eager to invest in fundamental science, to push the boundaries of knowledge and assert its technological prowess on the world stage. It was an era of big thinking, of moonshots and massive engineering projects. Unprecedented amounts of money flowed into building the tools of discovery, from particle accelerators that could probe the heart of the atom to giant telescopes that could look back to the dawn of time. It was in this fertile climate of scientific optimism that John Krauss, a professor of electrical engineering at The Ohio State University, saw an opportunity to realize a long-held dream. He had been captivated by Jansky's discovery as a young man and inspired by Grote Reber's pioneering work. During the war, he had made significant contributions to the development of radar, but his passion remained fixed on the cosmos. He dreamed of building a radio telescope of unprecedented scale, an instrument capable of not just listening to the Milky Way, but of conducting a comprehensive, definitive survey of the entire radio sky. He was an inventor as well as a scientist. He developed a unique, corkscrew-shaped antenna, the helical antenna, a design that would later prove essential for satellite communication. In 1952, with the help of his students, he built a small array of these antennas on a patch of university farmland. The survey was a success, but it only served to whet his appetite for something grander. He knew that to truly map the heavens, he needed an instrument of breathtaking size. His initial plans were almost fantastical, envisioning a telescope spanning 2,000 feet. Funding, as is so often the case in the pursuit of pure knowledge, was a limiting factor. His grand plans were scaled back, first to 720 feet, and then finally to a still massive 360 feet for the main parabolic reflector. In 1956, he secured a 20-acre plot of land and a grant from the National Science Foundation. The Ohio State University Radio Observatory was born, and with it, the ambitious project to build the great telescope that would affectionately come to be known as the Big Ear. The construction of the Big Ear was a monumental undertaking, a 5-year saga of ingenuity born from profound financial constraints. John Krause's grant was modest, far too small to hire a professional construction firm for a project of this magnitude. So, he turned to the most dedicated and affordable labor force he could find, his own volunteer graduate students, from 1956 to 1961. They toiled on the Ohio farmland, a small team of young scientists and engineers slowly bringing his unique, unconventional design to life. It was a telescope built not for elegance or for precision steering, but for one singular purpose: to be the most sensitive listening device on the planet for the least amount of money. The final structure was a marvel of minimalist engineering, a sprawling, static machine the size of 3 modern football fields. Its foundation was a vast, flat ground plane of aluminum mesh, 3 acres in extent, shimmering like a metallic lake. At one end stood a massive, curved parabolic reflector, fixed to the ground. At the other, a flat, tilting reflector, which could be adjusted to change the telescope's declination, its up and down aim into the heavens. Out in the middle of the aluminum field sat the feed horns, 2 large, scoop-like structures pointed at the parabola, designed to funnel the focused radio waves into the receivers. Unlike the sleek, steerable dish antennas of today, the Big Ear was largely immobile. It could not pan left or right to track an object across the sky. Instead, it relied on the steady, predictable, and free-of-charge rotation of the Earth to do the work. The operators would set the tilt of the flat reflector to a specific angle, and then, for 24 hours, the Earth itself would turn the telescope, sweeping its narrow beam across a thin, continuous strip of the sky. After a few days of patient observation, they would adjust the angle by a fraction of a degree and begin painting a new strip in this patient, methodical, and economical way. Over the course of years, they planned to create the first comprehensive map of the entire visible radio sky. When it was finally completed and brought online in the early 1960s, the Big Ear was one of the largest and most sensitive radio telescopes on Earth. Its initial purpose was not the speculative search for alien civilizations, but the foundational work of astronomical surveying. In those early days of the field, radio astronomy was still a young science, a frontier just beginning to be explored. While other astronomers had used smaller, more agile dish antennas to study specific stars or galaxies in detail, no one had yet undertaken a comprehensive, all-sky survey to catalog the myriad sources of radio emission. The Big Ear's team, led by Krause, were like the cartographers of old, charting a new, invisible continent. For the next decade, using an IBM computer with a now laughably small 16 kilobytes of memory, they meticulously collected, processed, and analyzed the data streaming from their giant instrument. The result was the Ohio All-Sky Survey, a monumental achievement in astronomy. They created a catalog of 20,000 cosmic radio sources, effectively doubling the number known to science at the time. They produced vast, detailed maps of the radio sky, a resource that would prove invaluable to astronomers around the world for decades to come. In the course of their survey, they discovered some of the most distant objects ever observed by any telescope, Quasars whose light had traveled for 12 billion years to reach them, offering a precious glimpse back to the universe's infancy, not long after the Big Bang itself. It was a period of profound and fruitful scientific contribution, a successful chapter that firmly established the Big Ear as a major instrument of discovery and a testament to the vision of its creator. But as the 1970s dawned, the scientific landscape began to shift. New, more advanced, and more expensive telescopes were being built, and the National Science Foundation, facing ever-present budget constraints, made the difficult decision to terminate funding for the aging Big Ear. In 1972, the official survey came to an end. The closure of one chapter, however, marked the beginning of another, one that would etch the Big Ear's name into history for a reason no one, not even its visionary builders, could have possibly predicted. Deep in the rolling, verdant hills of West Virginia, nestled within a valley deliberately shielded by the Allegheny Mountains, lies the Green Bank Observatory. It is a place of intentional, almost sacred quiet. Here, the air is not just clean of pollutants, it is electronically pure. By an act of Congress, the surrounding region is a national radio quiet zone, a 130,000 square mile bubble of silence, where the pervasive electronic cacophony of modern technology, cell phones, Wi-Fi, microwave ovens, even gasoline-powered cars is either heavily restricted or banned outright. This electronic tranquility is not a quaint preference. It is an absolute scientific necessity. Because Green Bank is home to some of the most sensitive radio telescopes in the world, including the magnificent Robert C. Byrd Green Bank Telescope, the largest fully steerable radio dish on the planet. The story of Green Bank, like that of the Big Ear, begins in the optimistic, ambitious post-war era of the late 1950s, as radio astronomy blossomed from a niche curiosity into a legitimate field of science. The United States recognized the need for a national observatory, a central facility that could house instruments larger, more powerful, and far more expensive than any single university could hope to build. The search began for the perfect location, a site that could provide the ultimate listening environment. The criteria were demanding a place with a very low population density, free from the electronic noise of power lines and cities, and ideally shielded by natural topography. After surveying dozens of sites up and down the East Coast, they found their ideal location in the secluded, isolated valleys of Green Bank. In 1957, the site was dedicated, and the first telescopes began to rise from the ground, great metal structures aimed at the silent heavens. Green Bank quickly became a pilgrimage site for the world's leading radio astronomers. They were drawn by the promise of access to the biggest and best instruments, and by the legally protected radio silence that allowed them to listen to the faintest, most distant whispers from the cosmos. Among them were a few bold scientists interested in a new, more speculative, and to some, more profound application of radio astronomy, the search for extraterrestrial intelligence, or SETI. One of these pioneers was a brilliant young astronomer named Frank Drake. In 1960, using one of Green Bank's then-new 85-foot telescopes, he conducted the first modern SETI experiment. He called it Project Ozma. For 200 hours over the course of several months, he painstakingly pointed the telescope at two nearby, sun-like stars, Tau Ceti and Epsilon Eridani, patiently listening for any signal that bore the unmistakable hallmarks of intelligent design, a signal that was narrow-band, focused, and artificial. He found nothing but the quiet hum of the cosmos, but the act of looking was itself a revolutionary step. It took the search for alien life out of the realm of science fiction and placed it firmly within the domain of legitimate, albeit long-shot, scientific inquiry. A year later, in 1961, Drake convened a small, now legendary meeting at Green Bank. He brought together a handful of the world's brightest minds, astronomers, chemists, biologists, and even a young, charismatic astronomer named Carl Sagan to have the first serious, structured discussion about the prospects for finding intelligent life elsewhere in the universe. In preparation for this historic meeting, Drake sought a way to frame the enormous problem, to give the discussion a rational, scientific structure. He began to jot down on a piece of paper the series of factors that would, in sequence, determine the number of detectable civilizations in our galaxy. He started with the rate of star formation. He then multiplied that by the fraction of those stars that have planets. Then, the average number of planets per star that could potentially support life. Then, the fraction of those planets on which life actually arises. Then, the fraction of life-bearing planets on which intelligence evolves. Then, the fraction of intelligent civilizations that develop technology capable of interstellar communication. And finally, he added the most enigmatic and sobering variable of all, L, the length of time such a communicating civilization might survive. He strung these 7 factors together into a simple-looking but profoundly complex formula that would become known as the Drake equation. It was never meant to provide a definitive answer. In 1961, most of its terms were complete unknowns, educated guesses at best. Its true purpose was to serve as a roadmap for the search, a powerful tool for organizing our ignorance and identifying the key questions we needed to answer to move forward. The equation itself is a beautiful and timeless piece of scientific reasoning. Decades later, it remains the fundamental framework for thinking about life in the universe. In the years since Drake first wrote it down, we have begun to make real progress on the early terms. Thanks to missions like the Kepler Space Telescope, we now know that planets are not rare, but common, with most stars in our galaxy hosting planetary systems. We are on the verge of being able to identify potentially habitable, Earth-like planets. But the later terms of the equation, those concerning the emergence of life, the evolution of intelligence, and especially the longevity of civilizations, remain shrouded in deep uncertainty. The final term, L, is a mirror held up to ourselves. We have only one data point for a communicating civilization, our own. How long will we last? A few centuries, a few millennia, a million years? The answer to that question dramatically alters the final result of the equation, determining whether the galaxy is teeming with active, ongoing conversations or is, instead, filled with the silent ruins and faint echoes of countless civilizations that have risen, shone brightly for a time, and then vanished. The Drake equation tells us, with chilling clarity, that the universe could be silent either because life is exceptionally rare, or because intelligent life is, as a rule, tragically self-destructive. With the closure of its official survey and the termination of its federal funding, the Big Ear Observatory faced an uncertain future, a slow decay into obsolescence. But a new purpose was emerging from the fringe of mainstream astronomy, inspired by the very questions being asked at places like Green Bank. Bob Dixon, the assistant director of the observatory, had attended a NASA-sponsored conference on Project Cyclops, a hugely ambitious conceptual design for a massive array of radio telescopes that would be dedicated to the search for extraterrestrial intelligence. The final report from that conference circulated widely, influencing a generation of young astronomers and solidifying the scientific case for a serious, sustained search. Dixon returned to Ohio with a bold idea. They had a world-class radio telescope, an instrument of immense sensitivity, sitting idle. They had a dedicated staff of engineers and students, a team of volunteers willing to continue the work out of pure passion. They could reconfigure the Big Ear, tune it for a new kind of signal, and dedicate it to the most profound search in human history. It would become the first large telescope in the world dedicated full-time to SETI. with no external funding, relying solely on the passion and ingenuity of its small team. They began the arduous task of transforming the instrument. The original all-sky survey had utilized wideband receivers designed to pick up the broad, chaotic, and noisy emissions of natural cosmic objects. But the search for an intelligent signal required a completely different approach. The prevailing theory, then as now, was that any civilization attempting to communicate across the vast, noisy distances of interstellar space would use a narrowband signal. Natural sources are like a shouting crowd, broadcasting across a wide range of frequencies, creating a cacophony of cosmic static. An artificial signal, however, would be like a single, clear, pure note played on a flute. A focused transmission at a single point on the radio dial, specifically designed to stand out against the overwhelming background noise of the universe. The team at Big Ear designed and built a new 50-channel receiver, a bank of 50 separate, highly sensitive radios, each tuned to a slightly different, very narrow frequency band, all centered around the 1,420 megahertz hydrogen line. In December of 1973, the Big Ear's second life, its true calling, began. For the next 4 years, it patiently scanned the skies, its great metallic ear turned to the heavens, listening for a single, clear note in the grand, cosmic symphony. On the clear, warm evening of August 15, 1977, the Big Ear was performing its silent, automated, and lonely vigil. The great flat reflector was tilted to its preset angle, and the Earth's steady rotation was slowly sweeping the telescope's dual beams across a strip of the night sky, passing through the dense star fields of the constellation Sagittarius. No one was at the observatory. The entire process was automated. A ghost in the machine. Incoming radio waves were collected by the giant reflectors, funneled into the feed horns, and processed by the IBM computer. The intensity of the signal on each of the 50 channels was measured every 10 seconds, translated into a simple alphanumeric code, and then diligently printed out, line by line, on long, continuous sheets of perforated paper. The system was a model of efficiency, designed to be run by a small team of volunteers with minimal oversight. A few days later, Jerry Amon, a volunteer professor from a nearby university, made his routine trip to the observatory. He collected the reams of printouts from the past several days and took them home for analysis. It was a methodical, often tedious task he performed several times a week, a quiet contribution to a grand search. After dinner, he would sit down at his kitchen table with the stacks of paper and begin the patient process of scanning the 50 columns of data. His eyes trained to look for anything out of the ordinary, any deviation from the expected background noise. Most of what he saw in those printouts was statistical noise. The expected random fluctuations of the cosmic microwave background, occasionally punctuated by the jagged, erratic spikes of recognizable interference from terrestrial sources like aircraft or distant military radar. It was a search for a needle in a cosmic haystack. But as he worked his way through the data from the night of August 15th, his eyes caught a sequence in one of the columns that made his heart stop. It was a pattern that was anything but random. In a single, narrow frequency channel, he saw the data begin to climb. The printout showed a 6. Then, on the next 10-second line, the intensity jumped to an E, the code for 14. Then it leaped to a Q, then a U, the code for 30, then a J, and finally a 5, before dropping back to baseline. The numbers and letters formed a steep, perfect crescendo, peaked dramatically, and then descended in a near-perfect mirror image of their ascent. It was the exact signature they had been hoping for, the unmistakable profile of a powerful, continuous celestial source passing directly through the center of the telescope's narrow beam. The intensity was staggering. At its peak, the signal was over 30 times stronger than the average background noise. It was, by an enormous margin, the most powerful and coherent signal the Big Ear had ever detected. Eamon knew immediately, with the certainty of a trained analyst, that this was not interference. Terrestrial interference is messy, erratic. It pulses on and off, creating jagged, ugly spikes in the data. This signal was smooth, elegant, a perfect Gaussian bell curve that precisely matched the theoretical shape of the telescope's antenna pattern as it scanned across a fixed point in the sky. It was as if something out there, in the direction of Sagittarius, had been waiting patiently for the Big Ear's gaze to sweep past it. In that singular moment of discovery, overwhelmed by the profound and almost terrifying implications of what he was seeing, Jerry Eamon grabbed a red pen, circled the incredible alphanumeric sequence 6EQUUJ5 on the printout, and in the margin, he wrote a single, emphatic, and now legendary word wow. The discovery of the wow signal triggered an immediate, intense, and private investigation. Eamon, Krauss, and Dixon began the rigorous process of scientific due diligence, their excitement tempered by a deep-seated skepticism. Their first and most important task was to try to eliminate every possible alternative explanation before even considering the extraordinary one. Could it have been an equipment malfunction? This seemed highly unlikely. The signal was detected with pristine clarity on only one of the 50 channels. A systemic glitch or malfunction would almost certainly have affected multiple channels at once, or produced a less coherent pattern. Could it have been a known natural source, like a planet, a star, or a distant galaxy? Krauss, the observatory's director, meticulously checked astronomical charts and catalogs. There were no known celestial objects in that specific patch of sky capable of producing such a powerful, and more importantly, such a narrow-band signal. Natural cosmic sources broadcast their energy across a wide range of frequencies. This signal was sharply focused. Could it have been an Earth-orbiting satellite? This was a more plausible, though still highly improbable, explanation. The signal was detected at a frequency of 1,420 megahertz. This frequency, known as the hydrogen line, is a universally significant frequency in astronomy because it is the natural emission frequency of neutral hydrogen, the most abundant element in the universe. Because of its profound scientific importance, this band of the radio spectrum is internationally protected by law. All terrestrial and satellite transmissions are strictly forbidden on it. For a satellite to be broadcasting illegally on this protected frequency was possible, but unlikely. Furthermore, a satellite would be moving across the sky at its own speed and trajectory. For its motion to have perfectly mimicked the steady, slow rotation of the Earth and produce that flawless 72-second-long bell curve was a statistical improbability of astronomical proportions. Could it have been a deliberate hoax? Only Eamon and Dixon had the technical access to the computer systems to manipulate the data in such a way. Both knew, with absolute certainty, that they had not. As they systematically ruled out each conventional explanation, the extraterrestrial hypothesis, as wild as it seemed, became more and more compelling. But there was a critical, confounding, and ultimately ambiguous piece of the puzzle. The Big Ear, with its unique and economical design, actually had two feed horns, two ears listening to the sky, situated side by side. This meant it had two beams. Any continuous celestial source, like a distant star or galaxy, would pass through the first beam. And then, approximately 3 minutes later, as the Earth continued to turn, it would pass through the second beam, producing two identical signals, separated by that 3-minute interval. This dual beam system was a brilliant, built-in mechanism for verifying signals and rejecting local interference. The WOW signal appeared with incredible, undeniable clarity in the first beam. But when the team, with bated breath, checked the data from the second beam, there was nothing, only silence. This fact added another profound layer of mystery to the event. For some, this was definitive evidence against an extraterrestrial origin, suggesting some sort of transient, one-off fluke, or a previously unknown type of terrestrial interference. For others, however, it made the signal even more exciting. It implied that the source was not a continuous, steady beacon. It had turned on, or perhaps its narrow beam had swept past us. During the 72 seconds it was in the view of the first horn, and then it had turned off, or its beam had moved on, before the second horn could catch it. A natural signal would not behave this way. An artificial signal, a deliberate, transient ping from a distant intelligence, very well might. For the next month, the big ear was repeatedly and deliberately aimed at that same patch of sky, listening intently for a repeat performance. For 70 days after that, it continued the vigil. Nothing was ever heard again. The signal had come and gone, leaving behind a single, unverified, and utterly perplexing artifact, a ghost in the data, a question mark hanging in the cosmos. The WOW signal quickly became a legend in the small, dedicated, and often maligned community of SETI researchers. It was a tantalizing glimpse of what might be possible, a ghost that fueled both hope and fierce debate for decades to come. But the broader scientific community, by necessity, remained deeply skeptical. A single, unrepeatable event, no matter how intriguing, does not constitute the extraordinary proof required for such an extraordinary claim. The scientific method demands verification without a second detection. The WOW signal was destined to remain an anomaly, a curiosity. The search required more than just listening. It required a robust framework for thinking, a way to quantify the vast, almost incomprehensible uncertainties involved. This is where Frank Drake's pioneering work at Green Bank provided the essential intellectual context. His equation, while not providing any concrete answers, served as a powerful tool for illustrating the immense scale of the challenge. To find a verifiable signal, a chain of countless low-probability events had to align perfectly. A planet had to exist in the right place, around the right kind of star. Life had to arise from non-life. That life had to evolve intelligence. That intelligence had to develop a technological civilization. That civilization had to not only choose to broadcast powerful signals into space, but it also had to survive its own technological infancy long enough for its signal to cross the immense, silent void and arrive at our solar system at the precise moment our telescopes happen to be pointed in the right direction, tuned to the right frequency. The search, as the Drake equation made starkly clear, was like searching for a single, specific, marked grain of sand on all the beaches of the entire world. And yet the possibility, however remote, was too profound, too central to our own quest for meaning, to ignore. The story of the WOW signal also inspired a different, more personal kind of search, one driven not by large institutions and government grants, but by individual passion and relentless curiosity. Robert Gray, a data analyst and amateur astronomer from Chicago, read about the signal in a small magazine published by John Krause in the late 1970s. He was utterly captivated by the mystery. He traveled to Ohio, visited the Big Ear, examined the original data printouts, and became convinced that the signal was a genuine candidate worthy of a serious, sustained follow-up. In the early 1980s, in a modern echo of Grota Reber's backyard pioneering, he built his own radio telescope, a 12-foot dish, and began his own, decades-long, largely solitary quest to find the signal again. He later gained access to professional telescopes, from the Oak Ridge Observatory at Harvard to the Very Large Array in the New Mexico desert, meticulously and patiently searching the small patch of sky where the signal had originated. He found nothing, but his lonely vigil highlights a crucial and often overlooked aspect of the WOW signal's enduring legacy, despite its fame and its tantalizing characteristics. The professional astronomical community never mounted a sustained, long-term effort to redetect it. The resources of big science are finite, and in a competitive field where progress is measured by verifiable, repeatable, and publishable results, a one-time, unconfirmed anomaly, no matter how spectacular, is often relegated to the status of a curiosity, a fascinating but ultimately unproductive footnote in the annals of science. Most professional SETI experiments, then and now, are designed to survey as many stars and as many frequencies as possible, spending only minutes, or even seconds, on any given target. The strategy is to cast the widest possible net in the cosmic ocean, but this entire approach is predicated on a significant assumption that a signal, if it exists, will be a continuous, unwavering beacon, shining brightly for anyone who happens to look. But what if that assumption is wrong? What if a truly advanced civilization, mindful of the colossal energy expenditure required for interstellar communication, would choose a more efficient, more patient strategy? The scenario of a directed, sweeping beam, like a cosmic lighthouse, offers a compelling and elegant explanation for the transient nature of the WOW signal. A civilization might not waste the astronomical amount of power required to broadcast a signal in all directions at once. Instead, they might use a powerful, highly focused antenna to ping a long, pre-compiled list of potentially life-bearing planets, targeting each one sequentially for a short duration before moving on to the next. They might send a pulse our way once a day, or once a year, or once a millennium. Our 72-second detection in this scenario would have been an incredible, almost impossible stroke of luck. A fleeting moment when our humble telescope happened to be looking in the right direction at the exact instant that an ancient, sweeping beam of light washed over our planet. This possibility completely reframes the meaning of the long silence that followed. It is not necessarily evidence of the signal's non-existence, but perhaps evidence of a different kind of communication strategy, one far more patient, more deliberate, and more energy efficient than our own. It transforms the search from a passive act of listening for a constant, steady drone into an active and far more challenging game of cosmic timing, waiting for a fleeting whisper that may not come again in our lifetimes, or even in the lifetime of our civilization. The WOW signal, viewed in this light, is not just a mystery to be solved, but a profound and humbling lesson in the potential nature of interstellar contact. It suggests that a conversation across the stars may not be a dialogue as we understand it, but a series of isolated, monadic messages, separated by gulfs of time and space so vast they challenge our very definition of what it means to communicate. The eventual fate of the Big Ear telescope is a poignant and perhaps inevitable epilogue to the story of its greatest and most enigmatic discovery. For 25 years after the detection of the WOW signal, it continued its dedicated SETI program, becoming, in the process, the longest-running, full-scale SETI project of its time. A feat recognized by the Guinness Book of World Records, it accomplished this almost entirely without federal funding. A remarkable testament to the unwavering dedication and passion of its small volunteer staff. But in the mid-1990s, the quiet patch of Ohio farmland on which it stood had become valuable real estate. Engulfed by the relentless spread of suburban development, a developer purchased the property with plans to expand an adjacent 9-hole golf course into a full 18-hole course and to build 400 new luxury homes. There was a public outcry, a desperate attempt by scientists and space enthusiasts to save the historic instrument. But the university, facing the prospect of long and expensive legal battles, chose not to fight. The telescope, in the eyes of many, had become obsolete. Its main reflector was frozen in place, its analog technology superseded by newer, more flexible, and more powerful digital instruments. In 1998, the demolition crews arrived. The giant metal structures were torn down, the vast aluminum ground plane ripped up and sold for scrap, where a massive, sensitive ear once listened to the deepest secrets of the cosmos. There are now manicured fairways, sand traps, and the quiet streets of a housing development. The demolition of the Big Ear is a stark and unsentimental symbol of the relentless nature of scientific and societal progress. Instruments, no matter how historic or significant, eventually outlive their usefulness. Science moves on. But there is a tragic and beautiful irony in its demise. If the WOW signal is ever confirmed to be a genuine extraterrestrial broadcast, the spot on Earth where humanity first heard the voice of another world will be nothing more than the seventh hole of a golf course. The end of the Big Ear, however, was not the end of the search. The torch was passed to a new generation of observatories, more powerful and more sensitive than John Krause could have ever dreamed. The primary heir to this legacy is the Green Bank Observatory. After facing its own existential funding crises in the early 2010s, when the National Science Foundation announced plans to divest from the facility, Green Bank found a new partner and a new, revitalized purpose. In 2015, a privately funded $100 million initiative called Breakthrough Listen was launched by the billionaire Yuri Milner, with the enthusiastic endorsement of scientists like Stephen Hawking and Frank Drake. The project's goal is to conduct the most comprehensive and sensitive search for extraterrestrial intelligence in history. To do this, it secured a significant portion of observing time on the world's most powerful radio telescopes, with the Green Bank telescope at the very heart of its operations. The search that began with Frank Drake's modest two-star Project Ozma has now evolved into a massive, data-intensive, global operation, Breakthrough. Listen scans millions of stars and billions of radio channels simultaneously, generating more data in a single day than all previous SETI projects combined over 50 years. The technology is vastly more sophisticated. The scope of the search is orders of magnitude larger, but the fundamental question remains exactly the same. We are still listening for a pattern in the noise, a single, clear, artificial note that stands apart from the deep, chaotic static of the cosmos. We are, in essence, searching for our own WOW signal, but this time, with instruments powerful enough to follow up immediately, to verify, to confirm, and to finally, perhaps, answer the question. And so we continue to listen. We persevere through the long, profound silence, through the persistent skepticism and the perennial funding challenges, because the stakes are simply too high to stop. The search is a strange and difficult kind of science, a field that demands the patience of a saint and the hide of a rhinoceros. A field where a lifetime of dedicated work may yield no positive results, where the only guarantee is the search itself. But it is driven by something deeper and more resilient than the scientific method alone. It is driven by a deep, innate, and universal human need for context. A profound desire to understand our own existence by learning if we are a singular, inexplicable miracle, or part of a vast, ancient, and unfolding cosmic community. The discovery of a single, verifiable signal would be a true inflection point in the history of our species. It would instantly and irrevocably transform our perspective, uniting every person on the planet with the shared, stunning knowledge that we are not alone. It might, in time, grant us access to knowledge far beyond our own, the accumulated wisdom of a civilization that has successfully navigated the same existential crises we now face. But even the silence, the great cosmic silence, has meaning. The Fermi paradox, if intelligent life is common, then where is everybody hangs over the entire endeavor like a shadow. The silence could mean that intelligent life is exceptionally, tragically rare. It could mean that we are, for all practical purposes, alone in our galaxy. It could mean that we are the first. And if that is the case, it bestows upon us an almost unbearable responsibility to survive, to cherish the fragile spark of consciousness we hold, and to become the voice that one day breaks the silence for others. We search because we are lonely. We search because we are hopeful. We search because the universe is vast and filled with unimaginable possibility, and the simple act of listening, of turning our collective attention outward to the great, quiet, and mysterious expanse, is one of the most profound and noble expressions of our own intelligence. It is, in the end, an act of faith in the possibility of connection, a quiet hope that somewhere across the unimaginable gulf of space and time, someone else is listening to. What if the key to time travel isn't hidden in the grandeur of massive spaceships or the elegant, theoretical curves of a wormhole, but in a realm so small, so counterintuitive, that it forces us to question the very fabric of reality? A world where particles can be in two places at once, where they defy our expectations of cause and effect, and where they can communicate instantaneously across vast cosmic distances. Welcome to the quantum realm, the strange and beautiful foundation of modern physics, and perhaps our most promising path to unlocking the profound mysteries of time itself. Quantum physics is not just a theory about the bizarre behavior of the tiniest constituents of matter. It is a field that is teeming with possibilities, with phenomena so complex and so contrary to our everyday experience that they have fundamentally reshaped how we think about space, about matter, and most tantalizingly, about time. Have you heard of quantum entanglement? The spooky action at a distance where two particles can remain mysteriously connected, their fates intertwined, no matter how far apart they are. Or have you contemplated the strange implications of retrocausality? The mind-bending idea that a choice made in the future could ripple backwards to influence an event in the past. These are not just concepts from the pages of science fiction. They are active areas of scientific inquiry, ideas that are pushing the boundaries of our understanding and hinting at the familiar linear rules of time we have always taken for granted might be just one limited perspective on a much deeper and far stranger reality. But time is not just an abstract scientific concept. It is the very rhythm of our lives, the relentless, forward-moving current that carries us from one moment to the next. Or does it? Could there be ways to slow it down, to speed it up, or even, perhaps, to reverse its flow entirely? The quantum realm, with its inherent uncertainty and its defiance of classical logic, introduces us to a world of bizarre and thrilling possibilities, from the potential to manipulate the very fabric of space-time to the exploration of alternate parallel realities. If you are ready to uncover how the strangest science of today could define the future of our relationship with time, then you are in for an exciting exploration. Together, we will break down the quantum mysteries that are reshaping our understanding of the universe, and we will venture into the incredible possibilities they offer. Welcome to this fascinating journey into the heart of quantum physics and the tantalizing dream of time travel. Time, as we experience it in the course of our lives, feels like a simple and straightforward concept. It is the steady, metronomic beat of an alarm clock that rouses us from sleep, the relentless ticking of seconds that turn into minutes, and minutes that turn into days. It is a seamless, linear progression, a universal ruler that we use to structure our existence, to measure our past, and to plan our future. But this intuitive, everyday experience of time as a steady and absolute march forward is a powerful illusion, a macroscopic simplification of a much more complex, more fluid, and more mysterious reality. To truly begin an exploration of time, we must first understand how our scientific conception of it has evolved. The classical view, most famously articulated by Isaac Newton, treated time as an absolute and universal constant. In the Newtonian universe, a single, master clock ticked at the same, unwavering rate for every object, in every corner of the cosmos. It was a fixed, unchanging background, a rigid stage upon which the drama of motion and force played out. But this comforting, clockwork picture of the universe was shattered in the early 20th century by Albert Einstein's theory of relativity. Einstein revealed that time is not absolute. It is relative. It is a dynamic and flexible dimension, inextricably woven together with space into a single, four-dimensional continuum called space-time. And this fabric of space-time is not a passive stage. It is an active participant in the cosmic drama, capable of being stretched, compressed, and warped by the presence of mass and energy. This warping of space-time is what we experience as the force of gravity. Time, in this relativistic picture, is a local phenomenon. The closer you are to a massive object, like a planet or a star, the more space-time is curved and the slower time flows. An atomic clock on a mountaintop will tick slightly faster than an identical clock at sea level. The astronauts on the International Space Station are aging a tiny fraction of a second slower than we are here on Earth. This effect, known as gravitational time dilation, is real and measurable. Similarly, the faster you move through space, the slower you move through time, a phenomenon known as velocity time dilation. A spaceship traveling at near the speed of light would experience time passing much more slowly than a stationary observer. For the astronauts on board, a journey that takes a few years could correspond to centuries or even millennia passing on Earth. Relativity revolutionized our understanding of time, transforming it from an absolute, universal constant into a dynamic, malleable dimension, intimately tied to the geometry of space and the motion of objects within it. But even this groundbreaking, relativistic view of time is now being challenged and deepened by the strange and often baffling world of quantum mechanics. Quantum mechanics throws a new and powerful wrench into our understanding of time, revealing a reality that is even more counterintuitive than the curved space-time of Einstein. At its core, quantum mechanics is a theory of probabilities and possibilities, not of certainties and definitive outcomes. The quantum realm is a hazy, indeterminate world, and this inherent ambiguity extends to the very nature of time itself. One of the foundational principles of quantum mechanics is the uncertainty principle. We often think of this in terms of position and momentum, but there is also a corresponding time-energy uncertainty principle. This principle suggests that the more precisely you try to measure the energy of a quantum system, the less precisely you can know the duration of that state, and vice versa, at the most fundamental subatomic level. Time is not a sharp, well-defined coordinate, but a fuzzy, blurred, and uncertain quantity. It is as if the universe, at its smallest scales, refuses to be pinned down to a single, definite moment. Another, even more profound. Quantum concept is superposition. A quantum particle, like an electron, can exist in a superposition of multiple, seemingly contradictory states at the same time, as long as it is not being measured. This raises fascinating, if highly speculative, questions about the nature of time. If a particle can be in a superposition of different locations or different energy states, could it, in some sense, be in a superposition of different moments in time? Could different timelines or different temporal possibilities coexist in a quantum state until a measurement collapses them into a single, experienced reality? While this is far from a mainstream scientific theory, it is the kind of mind-bending question that the strangeness of the quantum world forces us to ask. These quantum peculiarities provide the fertile ground from which new and often radical theories of time are beginning to emerge. One such idea is the block universe theory. This is a concept that has its roots in relativity, but it gains a new and deeper resonance in the context of quantum mechanics. In the block universe view, time is not a flowing river that carries us from a fixed past to an open future. It is a static, four-dimensional block of space-time in which all of time past, present, and future exists simultaneously and equally. Your birth. This very moment you are reading these words, and all the events of the distant future are all equally real, all just different coordinates in this frozen, four-dimensional landscape. In this picture, the flow of time is a subjective illusion of our consciousness, a trick of our perception as our awareness moves through this pre-existing block. Another, even more radical, idea is that time, as we perceive it, may not be a fundamental aspect of reality at all. It could be an emergent property, a macroscopic phenomenon that arises from the deeper, more fundamental, and perhaps timeless interactions of the quantum world, in the same way that temperature emerges from the collective motion of countless individual atoms. In this view, at the most fundamental level of reality, there may be no before or after, no arrow of time, only a complex network of quantum relationships. The time we experience is a kind of statistical thermodynamic illusion, a consequence of the fact that we are large, complex, and entropy-producing systems. Finally, the phenomenon of quantum entanglement, the spooky action at a distance where two particles can remain instantaneously connected across vast stretches of space, adds another layer of mystery to the quantum time conundrum. If this non-local connection can link particles across space, could a similar form of entanglement link events across time? Could a measurement made on a particle today be entangled with the state of a particle in the distant past or future? This is a highly speculative and controversial area of research, but it is one that is being actively explored by some theoretical physicists. It hints at a universe where the relationship between past, present, and future is far more complex and interconnected than our classical intuition would ever allow. From the uncertainty of quantum measurements to the timelessness of the block universe, from the emergent nature of time to the temporal possibilities of entanglement, quantum mechanics is not just challenging the simple, classical view of time. It is shattering it. And from the pieces, it is offering us the tantalizing clues to a new, deeper, and far more wondrous understanding of this most fundamental and most mysterious aspect of our reality. Imagine, for a moment, a particle approaching a solid wall. In our everyday classical world, the outcome is simple. If the particle does not have enough energy to break through or go over the wall, it will bounce off. The wall is an absolute barrier, but in the strange and counterintuitive world of quantum mechanics, this is not always the case. There is a small but non-zero probability that the particle can simply appear on the other side of the wall without having broken it and without having had enough energy to overcome it. This is the phenomenon of quantum tunneling. And it is not science fiction. It is a real, measurable, and essential feature of our universe. At its core, quantum tunneling is a direct consequence of the wave-like nature of quantum particles. A particle, like an electron, is not a solid, point-like object. It is a wave function, a cloud of probability that describes the likelihood of finding the particle at different locations. This wave does not stop abruptly at an energy barrier. It decays exponentially into it. If the barrier is thin enough, the wave function can have a small, but non-zero amplitude on the other side. This means that there is a finite probability that the particle, when measured, will be found on the far side of the barrier. Having seemingly tunneled through an impossible obstacle, it is as if the particle has momentarily borrowed the energy needed to overcome the barrier, thanks to the energy-time uncertainty principle passed through, and then repaid the energy on the other side. This unsettling, yet mesmerizing, behavior is not just a theoretical curiosity. It is a process that is happening all around us, and even within us. The sun shines because of quantum tunneling. In the immense heat and pressure of the sun's core, hydrogen nuclei are constantly colliding. Classically, they do not have enough energy to overcome their mutual electrostatic repulsion and get close enough to fuse together. But thanks to quantum tunneling, they have a small chance of bypassing this energy barrier, allowing the strong nuclear force to take over and initiate the process of nuclear fusion. It is this quantum leap that powers the sun and, ultimately, all life on Earth. Quantum tunneling is also at the heart of much of our modern technology. The transistors that are the building blocks of every computer and smartphone rely on the ability of electrons to tunnel through thin, insulating barriers in semiconductor materials. The flash memory that stores our data works by trapping and releasing electrons in a floating gate through a quantum tunneling process. Even some biological processes, like the way enzymes catalyze chemical reactions or the way our sense of smell works, are now thought to involve a form of quantum tunneling. The stark difference between the behavior of the quantum world and the macroscopic world of our everyday experience is a matter of scale and probability. While a single electron has a small but significant chance of tunneling through a thin barrier, a macroscopic object, like a basketball or a human being, is a collection of trillions upon trillions of particles. The probability of all of those particles tunneling through a solid wall at the same time is so infinitesimally, vanishingly small that it is, for all practical purposes, 0. We will never see a person walk through a wall, not because it is forbidden by the laws of physics, but because the odds are so astronomically against it that it would not happen even once in the entire lifetime of the universe. This scale-dependent nature of quantum effects is one of the reasons why the quantum world seems so strange and alien to us. Our intuition has been shaped by our experience in the macroscopic world, a world where probabilities have averaged out to become near certainties. But at the fundamental level, the universe is a game of chance, a world of probabilities and possibilities. Now, this is where the conversation turns towards the truly speculative and mind-bending. If a particle can tunnel through a barrier in space, could it, or perhaps the information it carries, tunnel through a barrier in time? This is a thrilling question that has captured the imagination of physicists and science fiction writers alike. While the concept of temporal tunneling is not a well-established scientific theory, it is the kind of what-if question that the strangeness of quantum mechanics invites us to ask. Could a particle tunnel from the present moment to a moment in the future? Bypassing the intervening time, could the information about a future event tunnel back to the present, giving us a form of precognition? These are ideas that are on the very fringes of theoretical physics, and they lack any experimental evidence. But they are born from a deep recognition of the parallels between space and time in modern physics. In Einstein's relativity, space and time are unified into a single, four-dimensional space-time. If quantum tunneling is possible in the spatial dimensions, it is not entirely illogical to ask if a similar phenomenon could be possible in the temporal dimension. For now, the boundary between science fact and science fiction remains clear. Quantum tunneling is a real, observed, and technologically crucial phenomenon that governs the behavior of particles in space. Its potential connection to time travel remains a purely hypothetical and deeply fascinating speculation. But the very existence of a phenomenon like quantum tunneling, a phenomenon that so profoundly violates our classical intuition, should give us a sense of humility. It is a powerful reminder that our everyday understanding of the world is a limited one, and that the universe, at its deepest level, operates according to a set of rules that are far stranger, more subtle, and more wondrous than we can yet fully comprehend. It is a call to keep questioning, to keep exploring, and to remain open to the possibility that the universe still holds secrets that could one day turn our most cherished scientific and philosophical assumptions on their head. Could a decision you make today ripple backwards through time to influence an event that has already happened? This is a question that seems to belong to the realm of paradox and fantasy. And yet, it is a question that physicists are forced to confront when they grapple with the strange and beautiful implications of delayed choice experiments in quantum mechanics. This is not about time travel in the classical sense of rewriting history. It is about something far more subtle and perhaps even more profound. It is about the strange and seemingly retroactive way in which our choices as observers appear to shape the reality of the quantum world. The story begins with the famous double-slit experiment. As we have seen, a single quantum particle, like a photon, will behave like a wave and create an interference pattern if we do not know which of the two slits it has passed through. But if we place a detector at one of the slits to gain this which path information, the photon behaves like a particle, and the interference pattern disappears. The act of measurement changes the outcome. In the 1970s, the brilliant and iconoclastic physicist John Archibald Wheeler proposed a thought experiment that took this strangeness to a whole new level. He asked, what if we delay the choice of whether or not to measure the which path information until after the photon has already passed through the slits? Imagine a setup where the photon has already gone through the double-slit barrier and is on its way to a detector screen. At the last possible moment, we can choose to either insert a set of detectors that will tell us which path the photon took, or to remove them and allow the interference pattern to form. Classical intuition would tell us that this choice should make no difference. The photon has already passed through the slits. Its behavior, whether wave-like or particle-like, should already be a fixed, historical fact. But this is not what happens. When Wheeler's thought experiment and its various more sophisticated versions have been carried out in real laboratories, the results have been consistently jaw-dropping. Even when the choice of measurement is made after the photon has passed through the slits, the outcome is the same. If the detectors are inserted, the photon is found to have behaved like a particle. If the detectors are removed, the photon is found to have behaved like a wave. It is as if the photon, in its journey, somehow knew what choice the experimenter was going to make in the future, and adjusted its past behavior accordingly. This is a result that is so counterintuitive that it can make one's head spin, but it is crucial to understand what it does, and does not mean. Delayed choice experiments do not imply that we can send information back in time, or that we can literally change the past. There is no paradox, no violation of causality. The trick lies in the subtle and holistic nature of quantum measurement. A quantum system, like our photon, is not a classical object with pre-existing properties. It is a wave function, a cloud of possibilities, and the reality we perceive is only defined in the context of the entire experimental setup, including the final act of measurement. The behavior of the photon is not an intrinsic property that it carries with it on its journey. Its waviness or particleness is a property of the whole system, of the relationship between the particle and the measuring device. To ask what the photon was doing before the final measurement is to ask a question that, from a quantum perspective, may not have a well-defined answer. As Wheeler himself famously put it, no elementary phenomenon is a real phenomenon until it is an observed phenomenon. The past at the quantum level is not a fixed and unchangeable record. It is an open, probabilistic story that is only finalized, only brought into being by the observations we make in the present. This is a profound and deeply unsettling idea. It challenges our most basic, classical understanding of time and causality. We are used to thinking of time as a linear sequence, where a cause in the past leads to an effect in the future, but the quantum world seems to hint at a more complex and more intertwined relationship between the past, the present, and the future. Some physicists, in trying to make sense of these results, have been led to entertain the radical idea of retrocausality, the notion that influences can, in some subtle quantum mechanical way, travel backwards in time. This is not about sending signals, but about a more fundamental, and as yet not fully understood, temporal symmetry in the laws of nature. The choices we make now may be part of a larger, self-consistent loop of causality that includes both the past and the future. But even without resorting to such radical ideas, the delayed choice experiment serves as a powerful reminder of the fundamental weirdness of the quantum world. It is a world where our common-sense notions of reality, of locality, and of time itself break down. And this has practical implications. The deep understanding of quantum measurement that has come from grappling with these paradoxes is essential for the development of quantum technologies. Quantum computers, for example, are built on our ability to precisely control and manipulate the delicate, superpositional states of qubits. The delayed choice experiment is a powerful tool for probing the very nature of this quantum state, for understanding how it is created, how it evolves, and how it is collapsed by the act of measurement. It is a mind-bending exercise in quantum logic, to be sure, but it is also a testament to the power of human curiosity, to our relentless drive to ask the deepest questions, and to our willingness to follow the evidence, even when it leads us into a reality that is far stranger, more subtle, and more beautiful than our classical minds could have ever imagined. The delayed choice experiment reveals the strange, retroactive influence of observation on a quantum system. But what if we could go a step further? What if we could not just decide whether to observe, but could also decide to forget what we have observed? This is the tantalizing premise of the quantum eraser experiment, one of the most bewildering and philosophically profound concepts in all of quantum mechanics. It is an idea that seems to be pulled directly from the pages of a science fiction novel, an experiment where the simple act of erasing information seems to rewrite a reality that has already happened. The story begins, once again, with the double-slit experiment. We know that if we measure which slit a photon goes through, we gain which path information, and this act of measurement destroys the wave-like interference pattern. The photon behaves like a particle. The quantum eraser experiment asks a simple, but audacious, question: what if we could erase this which path information after we have recorded it? Could we bring the interference pattern back from the dead? The setup for a delayed choice quantum eraser experiment is ingenious and complex. It typically involves a source that produces pairs of entangled photons. These photons are linked in such a way that they are a single, unified quantum system, even if they travel in different directions. One photon, the signal photon, is sent towards a double-slit barrier and a detector screen. The other photon, the idler photon, is sent along a different path to a separate set of detectors. The clever part is that the path of the idler photon can be used to determine which slit its entangled partner, the signal photon, went through. So, by measuring the idler photon, we are, in effect, measuring the which path information of the signal photon, even without directly interacting with it. And as expected, when we do this, the signal photons hitting the screen do not show an interference pattern. They behave like particles. But now comes the eraser part. The experiment is set up in such a way that we can make a choice about what to do with the idler photon. We can either measure it in a way that reveals the witch path information, or we can erase this information by sending the idler photon through a set of beam splitters that scrambles its path, making it impossible to know which slit its entangled partner went through. And here is the truly mind-bending twist. This choice of whether to erase the information can be made after the signal photon has already hit the detector screen. And when the experiment is performed, the results are stunning. If we look at the total pattern of all the signal photons on the screen, it is just a diffuse blob with no interference. But if we then look at our data and select only those signal photons whose entangled idler partners had their witch path information erased, a beautiful, clear interference pattern magically reappears. It is as if the future act of erasing the information has reached back in time to influence the past behavior of the signal photons, causing them to act like waves. At first glance, this seems to be a clear violation of causality, a form of retroactive rewriting of history. But as with all quantum paradoxes, a closer look reveals a more subtle and even more profound truth. The quantum eraser does not actually allow us to change the past. The key lies in the process of post-selection and the nature of entanglement. The interference pattern is not visible in the raw, total data. It is only revealed when we correlate the data from the signal photons with the data from the idler photons. It is a hidden pattern, a ghostly correlation that is only brought to light when we have the information from both parts of the entangled system. The choice we make in the future about the idler photon does not change what has already happened at the signal detector. It simply changes the way we are able to sort and interpret that past data to reveal a hidden, pre-existing quantum correlation. The story is self-consistent across time. There is no paradox. But the philosophical implications are still staggering. The quantum eraser experiment is a powerful demonstration of the holistic and non-local nature of quantum reality. It shows that an entangled system is a single, indivisible whole, and that its properties cannot be understood by looking at its parts in isolation. The behavior of the signal photon is inextricably linked to the fate of its distant, entangled twin, and the reality of the system is only fully defined when we consider the entire experimental setup, including the final measurements made on both particles. It is also a profound illustration of the deep connection between information and physical reality in the quantum world. The presence or absence of witch path information is not just a matter of our knowledge. It is a physical variable that has a direct and tangible effect on the behavior of the system. To erase information is not just a mental act. It is a physical act that can restore the wave-like, superpositional nature of a quantum system. The possible applications of this principle, while still largely theoretical, are tantalizing. The quantum eraser provides a powerful tool for exploring the fundamental nature of quantum measurement and decoherence, which is crucial for the development of robust quantum computers. The ability to control and manipulate quantum information, to erase it, and to restore quantum coherence could be a key ingredient in building fault-tolerant quantum memory and communication systems. But beyond any potential technological applications, the quantum eraser holds a deep and enchanting allure. It is a cosmic magic trick, a demonstration of the universe's ability to operate in ways that are far more subtle, strange, and interconnected than our classical minds could have ever conceived. It is a crack in our familiar worldview, a window into a deeper, more holistic, and more mysterious reality. A reality where the past, the present, and the future are bound together in a beautiful and paradoxical quantum dance. What if the familiar one-way street of time, the relentless march from cause to effect, is not a fundamental law of the universe, but a macroscopic illusion? What if, at the deepest level of reality, the future can ripple backwards to influence the past? This is the radical and mind-bending concept of retrocausality, an idea that is so counterintuitive that it seems to belong to the realm of fantasy, but which is being seriously considered by some physicists as a potential way to resolve some of the deepest paradoxes of quantum mechanics. At its core, retrocausality challenges our most basic and most cherished assumption about the nature of time, that causation is a one-way street. In our everyday world, events unfold in a clear, linear sequence. You drop a glass, and then it shatters. The cause precedes the effect. The idea that the shattering of the glass could somehow influence the act of dropping it is absurd. But in the strange, probabilistic world of the quantum, the rules of cause and effect are not so clear-cut. Retrocausality proposes that the relationship between events is not a simple, forward-moving chain, but a more complex, self-consistent loop, where influences can travel both forwards and backwards in time. This is not about sending messages to the past to change history. It is about a more subtle and more fundamental temporal symmetry in the laws of nature, a symmetry that is hidden from us in our macroscopic world, but which may be at play in the quantum realm. The idea of retrocausality has its roots in some of the earliest debates about the nature of quantum mechanics. It was proposed as a way to explain the spooky action at a distance of quantum entanglement without violating the principle of locality. In a retrocausal picture, when you measure one of a pair of entangled particles, you are not instantaneously influencing its distant partner. Instead, your measurement choice sends an influence back in time to the moment when the particles were first entangled, and this influence then travels forward in time with the other particle, ensuring that its measurement outcome will be correlated with yours. It is a strange and seemingly convoluted explanation, but it is one that can, in principle, reproduce all the predictions of quantum mechanics without any faster-than-light communication. More recently, retrocausality has found a new and fascinating playground in the context of the delayed choice and quantum eraser experiments. As we have seen, these experiments seem to show a future measurement choice, retroactively determining the past behavior of a particle. While these results can be explained without invoking retrocausality, by appealing to the holistic and non-local nature of the quantum state, a retrocausal interpretation offers a different, and for some, a more intuitive, way of thinking about the problem. It takes the apparent retroactivity at face value. The choice made by the experimenter in the future sends a real physical influence back in time to the double-slit barrier, telling the particle whether to behave as a wave or a particle. The past, in this picture, is not a fixed and unchangeable record. It is a pliable, dynamic entity that is constantly being shaped by its relationship with the future. It is crucial to emphasize that retrocausality, as it is currently understood, does not allow for the kinds of paradoxes that are so beloved of science fiction. You cannot send a message back in time to tell yourself the winning lottery numbers, or to warn your past self not to make a terrible mistake. The influences are thought to be at the level of the quantum wave function, shaping the probabilities of events, not determining their specific outcomes in a controllable way. The universe, in a retrocausal model, is still self-consistent. The future can influence the past, but only in a way that is consistent with the present. It is a closed, logical loop. The grandfather paradox, for example, is avoided because the universe would simply not allow for a self-contradictory history to be created. If you were to travel back in time to try and prevent your own birth, the retrocausal influences would conspire to ensure your failure. The gun would jam, the car would break down, your resolve would fail. The timeline is robust. This is a concept that is incredibly difficult to test experimentally. The influences are subtle, and they are woven into the very fabric of quantum probability. But theoretical physicists are actively working on developing new experimental protocols that could distinguish between a standard, forward causal quantum mechanics and a retrocausal one. The practical applications of retrocausality, if it is a real feature of our universe, are, at this stage, purely in the realm of speculation, but the philosophical implications are profound. It would mean that our understanding of time, of causality, of free will, and of the relationship between the past, the present, and the future would need to be fundamentally rewritten. It would suggest a universe that is not a linear, unfolding story, but a single, holistic, four-dimensional block of space-time, in which all of time exists at once, and the connections between events are not limited to a single, forward-moving direction. It would be a universe where the future is not just a passive consequence of the past, but is an active participant in its creation. The pursuit of these answers is more than just an intellectual exercise. It is a testament to the human capacity to question what once seemed unquestionable, to imagine realities that are far beyond our everyday experience, and to relentlessly probe the deepest and most fundamental mysteries of existence. Retrocausality is a bold and delicate idea, a whisper from the frontier of physics that hints at a universe that is far more strange, more interconnected, and more wondrously complex than we have ever dared to imagine. Quantum physics often feels like a puzzle that you can't quite finish. Each piece seems to promise a glimpse of a larger, coherent picture, but the edges never quite seem to align. For decades, one of the most confounding aspects of the theory has been the measurement problem, the question of what happens when we observe a quantum system, when the ghostly probabilistic world of superposition collapses into a single, definite reality. The traditional Copenhagen interpretation simply posited that this collapse happens without explaining how or why. This was a deeply unsatisfying state of affairs for many physicists. Then, in the 1950s, a young doctoral student at Princeton named Hugh Everett III came along with a proposal that was as audacious as it was elegant. He suggested that the collapse never happens. The quantum wave function, with all its superpositional possibilities, is the complete and final description of reality. And when a quantum event with multiple possible outcomes occurs, the universe itself splits into multiple parallel universes, one for each possible outcome. This is the many worlds interpretation of quantum mechanics, and it is an idea that, if true, would completely and utterly transform our understanding of reality. Imagine flipping a coin. In the many worlds view, the very act of flipping the coin does not lead to a single outcome of heads or tails. It leads to a branching of reality. A universe is created where the coin lands heads and another equally real. Universe is created where it lands tails. You, the observer, also split. One version of you sees the heads and another version sees the tails, and each version is completely unaware of the other's existence. In this picture, the entire history of the universe is a constantly branching tree of possibilities, a multiverse of parallel realities, where every quantum choice, every probabilistic event has led to the creation of a new world. The implications of this theory are breathtaking, and for many, deeply unsettling. It means that for every decision you have ever made, there is another version of you in a parallel universe who made the opposite choice. There is a universe where you took that job you turned down, a universe where you married your high school sweetheart, a universe where you caught that train you missed. Somewhere out there, in the vast branching landscape of the multiverse, all of your unlived lives are being lived out by other, equally real versions of yourself. It is an idea that is both exhilarating and dizzying, one that challenges our most basic assumptions about our own uniqueness and the nature of our own personal history. But how does this strange and wonderful idea of a branching parallel reality change our understanding of an even stranger concept? Time travel. The many worlds interpretation offers a beautiful and elegant solution to one of the most famous and intractable paradoxes of time travel. The grandfather paradox. The paradox, in its classic form, goes like this: if you were to build a time machine, travel back to the past, and prevent your own grandfather from meeting your grandmother, then your parent would never be born, and therefore you would never be born. But if you were never born, how could you have traveled back in time to commit the act in the first place? It is a logical contradiction that seems to make any form of time travel that can alter the past a physical impossibility. But in the many worlds interpretation, this paradox simply dissolves. When you travel back in time, you are not traveling into the past of your own specific branch of the multiverse. You are, in effect, crossing over into a different branch. When you interfere with the past in this new branch by, for example, preventing your grandfather from meeting your grandmother, you are not changing your own history. You are simply creating a new timeline, a new branch of the multiverse, one in which you were never born. But your original universe, the one from which you departed, remains completely unchanged. The version of you that built the time machine still exists, still has a grandfather, and still has a history. You have not erased yourself from existence. You have simply become a visitor, an orphan of time, in a parallel reality. The grandfather paradox is resolved because the cause and the effect are now in two separate, non-communicating universes. This makes time travel, at least in a theoretical sense, a much less dangerous and more self-consistent proposition. It is not an act of rewriting a single sacred timeline, but an act of exploring the vast, pre-existing landscape of parallel realities. It is less like editing a document and more like choosing to read a different book. But the many worlds interpretation, for all its elegance, does not come without its own set of challenges and complexities. For one, can we still call it time travel if you can never return to your original timeline? If every trip to the past is a one-way ticket to a new, alternate reality, then the very concept of returning to your own time becomes meaningless. And how would you navigate this infinite, branching tree of possibilities? If you wanted to travel to a specific past event, how would you pinpoint the exact branch of the multiverse you wanted to visit? The sheer, incomprehensible vastness of the possibilities, while exciting, also makes the idea of a controlled, targeted form of time travel seem dauntingly, if not infinitely, complex. And of course, the biggest challenge of all is the fact that the many worlds interpretation, like the broader concept of the multiverse, is at present unfalsifiable. We have no way to experimentally verify the existence of these other parallel universes. They remain, for now, beautiful and compelling mathematical constructs, born from the strange logic of quantum mechanics, but not yet a part of our confirmed empirical reality. And yet, the many worlds interpretation continues to be a popular and influential idea among many theoretical physicists. It is a testament to the profound and often uncomfortable places that our science can lead us. It is an invitation to confront the very limits of our own understanding, to reconsider everything we think we know about the nature of time, of choice, of identity, and of existence itself. It is a mind-expanding lens through which to view the universe, a lens that reveals a reality that is not a single, linear story, but an infinite, branching, and wondrously complex tapestry of all possible stories. And it is a reminder that, in the strange and beautiful world of quantum physics, the line between science and science fiction is often a very thin and very blurry one indeed. Imagine a world where time is not a linear, unyielding arrow, where the future does not just follow the past, but can loop back to influence it, where the very boundaries of causality blur into a surreal and beautiful dance. This is not the opening to a fantastical novel, but the foundation of a real and mind-bending concept in theoretical physics, the closed timelike curve, rooted in the elegant but often strange equations of Einstein's general theory of relativity. These theoretical pathways propose that the fabric of space-time may not be a simple, flat sheet, but can, under certain extreme conditions, bend and fold back on itself, creating loops in time. While the idea has its foundations in the classical, deterministic world of Einstein, its profound and paradoxical implications find their most fascinating expression when they intersect with the strange, probabilistic rules of the quantum realm. Today, we will explore this fascinating intersection, focusing on the scientifically grounded theories that are pushing the boundaries of our understanding of time, and offering us a tour through a universe that is far stranger and more compelling than any science fiction script. Closed timelike curves, or CTCs, first emerged as a possibility from certain exact solutions to Einstein's field equations. These equations describe how the presence of mass and energy curves the geometry of space-time. In most familiar situations, this curvature is gentle, leading to the familiar, forward-moving flow of time. But in some exotic and highly theoretical scenarios, the curvature can become so extreme that it creates pathways that loop back into their own past. Imagine tracing a path through the 4 dimensions of space-time that brings you back to your starting point, not just in space, but in time as well. This is a closed timelike curve. One of the first and most famous of these solutions was discovered by the brilliant logician and mathematician Kurt Gödel in 1949. He found that in a universe that is rotating as a whole, it would be possible for a sufficiently fast-moving spaceship to travel on a path that would return it to its own past. Later, the physicist Frank Tipler explored the theoretical construct of a Tipler cylinder, an infinitely long and incredibly dense rotating cylinder, which could also, in theory, generate CTCs around it. These models, while mathematically sound, are thrilling for the imagination, but they also raise profound questions about whether nature would ever allow such structures to form. They require conditions a rotating universe, an infinite cylinder that do not seem to correspond to the cosmos we observe. But beyond their theoretical elegance, closed timelike curves force us to confront the great paradoxes of time travel. If such a pathway through time exists, could an object or a person journey into their own past? This possibility immediately opens the door to the grandfather paradox, a time traveler who goes back and interferes with the past in a way that prevents their own existence. For example, by preventing their grandparents from ever meeting, creates a logical contradiction that seems to make such a journey impossible. For a long time, this was seen as a powerful argument against the physical possibility of time travel. And yet, the mathematics of general relativity does not explicitly forbid the existence of CTCs. This has left physicists to grapple with a deep and perplexing question: do these paradoxes represent a fundamental flaw in our understanding of time? Or is there a deeper, and perhaps quantum principle at play that resolves them? The creation of a closed timelike curve, even in theory, is not a simple matter. The mathematical models that allow for them typically require the existence of exotic matter, a hypothetical form of matter with a negative energy density. This is a substance that would have bizarre anti-gravitational properties. And it is something that has never been observed in nature, while some subtle quantum phenomena, like the Casimir effect, can create localized regions of negative energy. The existence of a macroscopic, stable form of exotic matter remains highly speculative, and may be forbidden by the fundamental laws of physics. The energy requirements to warp space-time into a loop are also astronomically high, far beyond anything our current, or even foreseeable, technology could ever achieve. But this is where the strange and beautiful world of quantum mechanics offers a new and intriguing avenue of exploration. Unlike the deterministic framework of classical physics, where an object has a single, definite history, the quantum world is a realm of probabilities and uncertainties. This has led some physicists to propose that the paradoxes of time travel might be resolved, not by forbidding CTCs, but by applying the rules of quantum mechanics to them. This is the idea of quantum self-consistency. In a quantum model of a CTC, a particle traveling on a time loop does not have a single, classical trajectory. It has a wave function, a superposition of all possible histories. The principle of self-consistency, most famously formulated by the physicist David Deutsch, proposes that the only histories that are allowed are those that are self-consistent. The particle can interact with its own past, but only in a way that does not create a logical contradiction. For example, in a quantum version of the grandfather paradox, a particle sent back in time to flip a switch that would prevent its own creation would not have a definite outcome. It would exist in a superposition of states, and the probabilities of the different outcomes would adjust themselves in such a way that no paradox is created. The probability of the particle successfully flipping the switch would be exactly balanced by the probability of it failing, leading to a self-consistent, if probabilistic, solution. This is an elegant and deeply quantum way of resolving the paradoxes. It suggests that the universe has a built-in, probabilistic censorship mechanism that prevents logical contradictions from ever occurring. Researchers have even begun to test these ideas using quantum computers to simulate the behavior of a qubit traveling on a closed timelike curve. These simulations have confirmed the predictions of Deutsch's model, showing that a self-consistent solution can always be found without any need to invoke a paradox. What's even more fascinating is that these simulations have shown that a qubit interacting with its past self through a CTC can gain extraordinary computational power, allowing it to solve certain problems that are thought to be intractable for even a standard quantum computer. This has led to the speculative, but tantalizing, idea that nature might be using the logic of closed timelike curves at some deep, hidden level of reality. As captivating as these ideas are, it is crucial to remember the immense challenges that lie ahead. To date, there is no experimental evidence for the existence of closed timelike curve. The exotic solutions of general relativity that contain them remain mathematical curiosities, tied to highly specific and often physically unrealistic conditions. Our technological capacity to manipulate space-time, which would require the harnessing of exotic matter or the generation of cosmic-scale energies, is nowhere near what would be needed to create a time loop in the laboratory. And even within the realm of quantum mechanics, while the simulations are intriguing, the practical implementation of a system that could genuinely send a particle on a journey into its own past remains light years away. These considerations underline a humbling truth about our current understanding. We are like children, just beginning to learn the alphabet of a deep and complex cosmic language. But in the gaps of our knowledge, in the tension between the classical and the quantum, lies the source of our greatest inspiration. The study of closed timelike curves is more than just an ambitious quest to build a time machine. It is a powerful intellectual tool that forces us to rethink the fundamental laws that govern space, time, and causality. It compels us to confront the deep and unresolved conflict between the deterministic, geometric world of Einstein and the probabilistic, superpositional world of the quantum, and in doing so, it is pushing the boundaries of human knowledge, unlocking profound new insights into the very nature of reality itself. Whether through the refinement of our theories of general relativity, the advancement of quantum computation, or the revolutionizing of our cosmological models, the research into closed time-like curves is creating ripples that are felt across multiple disciplines, shaping the trajectory of scientific discovery for generations to come. Each new exploration, each new thought experiment, brings us a little closer to answering the foundational questions that have defined the human quest for understanding for millennia. And it is a bold and beautiful reminder of the audacity, the creativity, and the enduring wonder that lies at the very heart of the scientific exploration of the cosmos. The dream of time travel, of breaking free from the linear confines of our own existence, has been a powerful and persistent theme in human culture for centuries. But could this dream ever move from the realm of fiction into the world of scientific fact? While the idea of building a macroscopic time machine remains firmly in the realm of speculation, some of the most advanced and mind-bending theories in modern physics are beginning to provide a theoretical and perhaps even a quantum blueprint for how such a feat might one day be possible. The journey begins with the strange and beautiful geometry of space-time, as described by Einstein's theory of general relativity. As we have seen, this theory allows for the theoretical possibility of wormholes, or Einstein-Rosen bridges, hypothetical tunnels through the fabric of space-time that could connect two very distant locations, or even two different moments in time. The problem is that these cosmic shortcuts are predicted to be incredibly unstable, collapsing in on themselves almost instantly. To keep a wormhole open long enough for something or someone to pass through would require a form of exotic matter, a substance with a negative energy density that could prop open the throat of the wormhole, counteracting the immense gravitational forces that are trying to crush it. For a long time, this was seen as a fatal flaw in the idea of traversable wormholes. But the quantum world, with its strange and counterintuitive rules, may offer a solution. At the heart of quantum mechanics lies the concept of quantum fluctuations, the incessant energetic ripples that occur even in a perfect vacuum. These fluctuations, a direct consequence of the uncertainty principle, can give rise to localized regions of negative energy. The Casimir effect is a direct, experimental demonstration of this phenomenon. While the amount of negative energy produced in the Casimir effect is tiny, it proves that the concept is not just a mathematical fantasy. The challenge, then, is to find a way to generate and control a sufficient amount of this quantum negative energy to stabilize a macroscopic wormhole. This is a technological hurdle of almost unimaginable proportions, but it is one that has shifted the problem from a matter of fundamental physical impossibility to a matter of extreme, but perhaps not insurmountable, engineering. This is where the power of quantum computing may one day come into play. Quantum computers, with their ability to simulate complex quantum systems, are becoming an essential tool for exploring the strange and wonderful world of quantum gravity. They allow researchers to model the curvature of space-time, the behavior of quantum fields in extreme gravitational environments, and the very nature of the quantum vacuum itself. As these machines become more powerful, they may allow us to test our theories of wormhole stability and to explore the properties of exotic matter in a virtual computational laboratory. This could lay the theoretical groundwork for understanding how to manipulate spacetime in a controlled and predictable way. Another, even more speculative, but equally fascinating, quantum phenomenon that could have implications for time travel is the time crystal. A regular crystal, like a diamond or a snowflake, is a structure whose atoms are arranged in a repeating pattern in space. A time crystal. A concept first proposed by the Nobel laureate Frank Wilczek in 2012 is a structure whose lowest energy state is one in which the constituent particles are in a periodic, repeating motion. It is a system that spontaneously breaks time translation symmetry. In a sense, it has a built-in perpetual clock. What is truly remarkable is that this perpetual motion does not require any input of energy and does not violate the laws of thermodynamics, as it occurs in the system's ground state. The existence of time crystals was experimentally confirmed in 2016, a stunning demonstration of a new and exotic state of matter. The practical applications of time crystals are still being explored, but they could have profound implications for quantum computing, for high-precision timekeeping, and perhaps even for our understanding of the nature of time itself. Could a time crystal, with its stable, repeating temporal loop, be used to anchor or stabilize a closed timelike curve? Could it be used to create a localized region of space-time where the normal linear flow of time is disrupted? These are ideas that are on the very edge of theoretical physics, but they are a beautiful example of how the discovery of new, exotic quantum phenomena can open up entirely new avenues of thought. Finally, the strange, non-local connection of quantum entanglement may offer yet another, and perhaps the most profound, pathway to rethinking our relationship with time. The EREPR conjecture, a bold and beautiful idea proposed by physicists Leonard Susskind and Juan Maldatina, suggests a deep and unexpected equivalence between two of the strangest concepts in modern physics, quantum entanglement and wormholes. The conjecture posits that every pair of entangled particles is, in some deep, geometrical sense, connected by a microscopic wormhole. This is a mind-bending idea, one that suggests that the strange, non-local connection of entanglement is not a spooky, disembodied action at a distance, but has a real, physical and geometrical manifestation in the structure of space-time itself. It suggests a deep unity between the laws of quantum mechanics and the laws of general relativity. A hint that these two great theories are just two different descriptions of the same underlying reality. Does this mean we can use entanglement to travel through wormholes? Not in any simple sense. The wormholes in the EREPR conjecture are thought to be non-traversable. But the idea that the very fabric of space-time is woven from the threads of quantum entanglement is a revolutionary one. It suggests that if we could learn to manipulate and control large-scale, multi-particle entanglement, we might, in effect, be learning to manipulate and control the geometry of space-time itself. This is the ultimate, and perhaps the most ambitious frontier in the quest for a quantum time machine. It is a quest that is no longer just about building bigger spaceships or finding cosmic shortcuts. It is about understanding and harnessing the deepest, most fundamental, and most mysterious properties of the quantum world itself. It is a journey that will require leaps of imagination, of experimental ingenuity, and of theoretical brilliance. And it is a journey that, whether it ultimately succeeds in building a time machine or not, is already transforming our understanding of the universe, and our own. Strange and wonderful place within it. The dream of traveling through time, of breaking the chains of the linear present, has long been a powerful and enduring part of the human imagination. But could this dream ever be more than just a dream? Could the strange and beautiful laws of quantum mechanics provide a key to unlocking the mysteries of time itself? The phenomenon of quantum entanglement, the spooky action at a distance that so perplexed Einstein, lies at the very heart of this inquiry. Entanglement describes a profound and mysterious connection between two or more particles, a bond so deep that their fates remain intertwined. No matter how far apart they are separated in space, a measurement on one particle instantly influences the state of the other. For a long time, this was seen as a bizarre, but ultimately limited, Feature of the quantum world. A strange correlation that could not be used to send information faster than light. But in recent years, a new and radical idea has emerged, one that suggests that this spooky connection may have a deep and unexpected relationship with the very geometry of space-time. This is the ER=EPR conjecture, a bold and beautiful hypothesis that proposes a fundamental equivalence between quantum entanglement and wormholes. It is an idea that suggests that every pair of entangled particles is connected by a tiny, microscopic wormhole, a shortcut through the fabric of space-time. This is not to say that we can simply entangle two particles and then crawl through the wormhole that connects them. The wormholes in the EPR conjecture are thought to be non-traversable. They are more like a private, quantum information channel than a physical tunnel. But the conjecture itself is revolutionary. It suggests that the strange, non-local connectivity of the quantum world and the dynamic, geometric structure of the relativistic world are not two separate things, but are two different descriptions of the same, underlying reality. The very fabric of space-time, in this picture, may be woven from the threads of quantum entanglement. The universe is not a classical, geometric stage upon which a quantum drama plays out. The stage and the actors are one and the same. This has profound implications for our understanding of time. If the geometry of space-time is emergent from the quantum state of the universe, then time itself may be an emergent phenomenon, a property that arises from the complex web of entanglements that connect all the particles in the cosmos. This could provide a new way to think about the arrow of time, the forward flow of time. The increase of entropy may be related to the increasing complexity of the entanglement structure of the universe as it evolves. And it opens up the tantalizing, if highly speculative, possibility that by manipulating entanglement, we could, in a sense, be manipulating the structure of time itself. The EPR conjecture is still a theoretical idea, one that is on the cutting edge of research in quantum gravity. But the connection between entanglement and space-time is not just a matter of abstract theory. It is being probed in real and increasingly sophisticated laboratory experiments using quantum processors, the powerful new machines that can control and manipulate the quantum states of individual particles. Scientists are now able to simulate the behavior of quantum systems in curved space-time, and even to create laboratory analogs of wormholes and black holes. In one groundbreaking experiment, researchers at Google, in collaboration with physicists at Caltech, used their Sycamore quantum processor to create a simulation of a traversable wormhole. They did this by creating a highly entangled state between two sets of qubits on their chip and then sending a quantum signal from one set to the other. They found that the signal propagated in a way that was consistent with the signal having traveled through a wormhole in a holographic toy model of a universe. This was not a real wormhole in physical space. Of course, it was a simulation, a quantum computation. But it was a stunning demonstration of the deep connection between the mathematics of quantum entanglement and the physics of space-time geometry. It was the first experimental realization of the idea that the dynamics of a gravitational system can be emergent from the quantum information processing of a non-gravitational one. These are early days, and the technological challenges are immense. Creating and maintaining the large-scale, highly entangled quantum states needed to test these ideas with precision is a colossal experimental hurdle. The fragility of quantum coherence, its susceptibility to decoherence from the surrounding environment, is a constant battle for quantum engineers. But the progress is rapid. And as our quantum technologies become more powerful, as we learn to control and manipulate the strange and beautiful world of entanglement with ever greater precision, we will be able to probe these deep connections between the quantum and the cosmos in new and profound ways. The potential implications are too enticing to ignore. If the link between entanglement and space-time is a real physical feature of our universe, could we one day learn to harness it? Could we create and stabilize a macroscopic, traversable wormhole by creating a specific, highly entangled state of matter and energy? Could we use the non-local connections of entanglement to create shortcuts, not just through space, but through time? These are questions that are on the very edge of our current scientific understanding. They are questions that may not be answered in our lifetimes. But they are questions that are no longer confined to the realm of science fiction. They are being asked and explored in the laboratories and on the blackboards of some of the world's leading physicists. The quest to understand the link between quantum entanglement and space-time is one of the most exciting and ambitious frontiers in all of science. It is a quest that promises to unify our two great theories of the universe, and in doing so, to reveal a reality that is far deeper, more mysterious, and more wondrously interconnected than we have ever dared to imagine. The idea of traveling backwards in time, of revisiting the past, is a concept that is fraught with paradox. The infamous grandfather paradox, in which a time traveler alters the past in a way that prevents their own existence, has long been seen as a fundamental, logical barrier to any form of time travel that can change history. But the strange, probabilistic nature of the quantum world may offer a way out, a way to have time travel without the paradoxes. This is a concept that is now being explored, not just in thought experiments, but in real laboratory simulations using some of the most advanced quantum computers in the world. Imagine a particle, a single qubit, traveling on a closed timelike curve, a path through space-time that loops back into its own past. In a classical world, this would be a recipe for paradox. If the particle is sent back in time to flip a switch that prevents it from ever being sent, we have a logical contradiction. But in the quantum world, the particle is not a classical object with a definite state. It is a wave function, a superposition of all its possible states. And according to the self-consistency principle proposed by David Deutsch, the only histories that are allowed on a CTC are those that are self-consistent. The universe, in a sense, edits out the paradoxes. Quantum simulations of this process, carried out by teams at IBM and Google using their powerful quantum processors, have shown how this can work in practice. They have successfully modeled the behavior of a qubit navigating a simulated CTC, and they have found that the quantum system naturally avoids paradox. The probabilities of the different outcomes of the qubit's interaction with its past self adjust themselves in such a way that no logical contradiction is ever created. It is as if the universe has a built-in probabilistic censorship mechanism. This is a stunning result. It suggests that time travel into the past may not be as logically impossible as we once thought. The quantum world, with its inherent fuzziness and its superposition of possibilities, seems to have a natural resilience to the paradoxes that would plague a classical time traveler. These experiments have also revealed something else that is equally profound, the concept of retrocausality. In these simulations, the state of the particle seems to be influenced by the measurement that will be made on it in the future. The choices of the experimenter seem to ripple backwards in time to shape the behavior of the particle in the past. This is not to say that information is being sent back in time in a controllable way. The outcome of any single measurement is still random, but the statistical correlations between the measurements show a clear and deeply strange retrocausal pattern. The future, in some subtle quantum mechanical way, seems to be reaching back to co-create the past. These advances in our ability to simulate the strange temporal dynamics of the quantum world are turning what was once pure speculation into a field of active experimental research. The notion of retrocausality, the idea that effects can precede their causes, is no longer just a philosophical curiosity. It is a concept that is being tested and explored In controlled laboratory settings, these simulations are showing that a retrocausal quantum mechanics can be fully self-consistent. The particles in these models seem to anticipate the future measurements that will be made on them, but they do so in a way that never violates the overall integrity and logical consistency of the system. This elegant, self-organizing property of quantum systems is a testament to the deep and often hidden logic that governs the universe at its most fundamental level. The role of quantum entanglement in these scenarios is crucial. When particles are entangled, their fates are linked, no matter how far apart they are in space or, perhaps, in time. This non-local connection may be the key to enforcing the self-consistency of the universe. It is as if the entangled particles are in constant, instantaneous communication, negotiating their shared reality to ensure that no paradoxes are ever created. This interconnectedness raises deep questions about the very nature of time itself. Is time an emergent property, something that arises from the deeper, more fundamental reality of the quantum state of the universe? In our everyday macroscopic world, time appears to be a linear, forward-moving arrow. But this may just be a consequence of the scale at which we operate, a statistical effect that emerges from the countless random interactions of the quantum world. At the fundamental quantum level, the distinction between past, present, and future may be far more blurry, more interconnected, and more dynamic than we can ever directly perceive. The interface between quantum computing and these deep theoretical questions is creating a new and exciting era of exploration. Companies like IBM and Google are not just building more powerful computers, they are building laboratories for probing the very foundations of reality. Their quantum processors, with their ability to handle the immense complexity of quantum simulations, are allowing researchers to explore the strange temporal landscapes of closed time-like curves and retrocausality in a way that was previously unimaginable. These simulations are exposing the limitations of our classical, intuitive understanding of time and causality. They are forcing us to confront a reality that is probabilistic, non-local, and perhaps even temporally symmetric. And in doing so, they may be providing us with the first tentative clues to a new and more unified understanding of the universe. A theory of quantum gravity that can finally reconcile the two great pillars of modern physics. The exploration of quantum time travel is more than just a quest to build a fantastical machine. It is a journey into the very heart of the quantum mystery. A journey that is challenging our deepest assumptions, expanding our intellectual horizons, and revealing a universe that is far more strange, more beautiful, and more wondrously interconnected than we have ever dared to dream.